The name of this video is Electric Dipole Interaction Net Torque. So in the previous video, we investigated the net force when we somebody builds an electrostatic or an electric ideal dipole, so that we have, as always, a negative charge at the distance dr from a positive charge. This distance is dr, ideal case, rigid body, from minus to plus dr, and we assume to observe from a certain point O in space such that this distance is r, and this distance is r plus dr. Parallelogram rule. Okay. We know that this dipole is embedded in an external field such that there is a field here, E at r, and a field here, E at r plus dr. Great. So with this in mind, how do we compute the torque gamma with respect to this origin? Now the origin counts, so we want to compute gamma, the net torque, with respect to this origin for this system. Well, we need to take r, cross it with the force F minus, which is the force acting on minus Q, plus r plus dr, which is this from O, distance from O, of plus Q, therefore times the force F plus acting on the positive charge, obviously. Okay, so this is what we get. Now, we know that these forces can be rewritten in terms of fields, so this gamma O can be rewritten as minus Q, because it's F minus, R crossed with E. Simply E and R, okay? That's specified, not to forget. Okay? Then here we have plus Q, because it's F plus Q, R. So this quantity here, actually we need to rewrite it. So let's spell it out. So it's going to be R plus dr. And what is this force? Is plus QE and R plus dr, but the R plus dr, we can rewrite it as E and R plus dE. Like this, okay? Because with this, we can rewrite it as E by tailoring it at R plus D. And we know that the total force from before, let's remind ourselves that the total net force is equal to QD. Okay, this is my total net force from the previous video. Okay, so now we can do this product. Let's forget about the E is function of R, we'll just call it E for simplicity. So gamma with respect to the origin O is given by minus Q R cross E from this one. QR, this one of course is also crossed here. This is crossed. So it's QR cross E plus QR plus cross E. So these two cancel out eventually, because here is also crossed. So these are all crossed. This is crossed and this is crossed. Okay, and don't forget that. So cross product, of course, is the torque. So QR cross E plus another QR cross D plus Q dr cross E plus Q dr cross D. Now let's keep in mind that F is equal to QD, and also we know that Q dr is equal to P, the dipole moment for an ideal electrostatic dipole or electric dipole in general. So this cancel out, QR cross E plus QR cross E, they cancel out. So we are left with three terms, which we can write up here. So the terms will be QR cross DE, but QR is P. So it's P cross DE. So this is from this term here. Then this actually, I apologize. This one, it's, let me do it in order. This one is the second term. So let me erase it and let me go in order. Let me not jump things. So the first one is not dr, it's r. So qdr is p. R, it's not p. So this I can take q next to d. So r vector qd is actually f. So this is r vector f. It's r vector f. I need to be careful not to confuse r's and dr's as I've done. Okay, this one is qdr, which is p vector e. And finally, this is qdr, which is p vector d. So let me repeat it, not to make confusion. QR is not P because it's not DR, QDR is P. So QR, vector E. QDE is F. So this is R vector F. And F we found it is the net force we found in the previous video. Okay, so this is the net force. Great. QDR is actually P vector E, P vector E. QDR is P vector D. Now, clearly, this one is higher order, so we can cancel it because it's DE. And so I'm left only with gamma naught equal R vector F, which is just the moment, the torque due to the net force F when I choose O as the origin, plus something which depends on both P and E, P vector E. Okay. Now, this is the result of the torque we wanted to find with respect to this origin O. Now, suppose that I choose as the origin a different origin. So if I choose O to coincide with Q minus, which I can do, then in this case, it so happens that gamma vector with respect, and of course this one is also a vector, with respect to Q minus, in this case, clearly R becomes 0 if I choose this new origin, because O coincides with minus Q here, and therefore I'm only left with P vector E, dipole moment vector E, which is quite interesting. So, as I said in the previous video, if the field is uniform, then there cannot be an F net, because D is 0 in the neighborhood of the dipole. So if in the neighborhood of this dipole, the external field, okay, remember that there is an external field E acting on this dipole, if this is uniform, the net force is 0. In that case, the only thing that mechanically acts on the dipole as a rigid body is actually this moment, this torque here. Of course, if the field is non-uniform, you need to write down all the cardinal equations of mechanics, which comprise the net force, which is non-zero, as well as the torque. Now, let's examine for a second the case where the field is uniform. So suppose that, for simplicity, E is uniform, in which case, clearly dE is equal to 0, no gradient. Therefore, the total net force F is clearly equal to 0. So the only thing that mechanically acts, I'm only interested in gamma, let's say with respect to Q minus, equal P vector E. This rules the entire dynamics, mechanically speaking, of this object. Okay, so what is interesting is that here this is a vector product. Therefore, if the two, so what happens is that if there are no other actions, mechanical actions on the dipole, so there is only the external field vacuum in the dipole and no other mechanical action, then clearly what happens is that if I begin with the dipole in this direction, so this is my dipole P, and this is my field E, with a certain angle here, alpha. Well, what happens is that if you solve the dynamic equation associated with this moment, which you should know from basic mechanics, well, I urge you to do that. So in Piazza, do the full mechanical calculation, calculate the dynamics. This is an interesting problem. So you do that in Piazza for me, okay? Basic mechanics. If you do that, you will find out that this dipole starts to move until the P and E become parallel, in which case this cross product becomes 0. Now, there are two configurations, actually, when this is true. So there is the parallel configuration, in which case P and E are parallel. So this is my E, and this is my P. Okay? They're parallel to each other. Okay? And E in general can be larger. They're not equal. Okay? As long as they're parallel, in that case, the sign of alpha becomes 0. And so, because it's the sign of 0. So this is the parallel case. And the other case is anti-parallel. This is actually a very interesting case. So in the anti-parallel case, we have P going in this direction. The sign is still 0. And E goes in this direction. Now, what is interesting is, in both cases, everything stops, the dynamic stops. Okay, they're either aligned or anti-aligned, the dynamic stops. However, in the parallel case, if you've done in mechanics stability, this is a stable case. Whereas this is an unstable case. And you can prove it mathematically with the stability criteria if you want. But in brief, it's kind of easy to believe this, because here, a little displacement, what it does, it will immediately make the dipole tend to become parallel. So in the parallel case, if they are parallel, any small displacement will result in small oscillations which eventually go back quickly to the stable position. If it's anti-parallel, any small displacement and a little kick I do to the dipole, it will start to make it rotate until eventually it goes parallel. Okay, so this is an unstable and this is a stable condition. And you can look really at the dynamics. You can solve it and also look at the criteria for stability criteria, which perhaps you have done in some mechanics course, or you will do it at some point in time. So to summarize this video here, electric dipole interaction net torque is the series of 3 videos. The first was the net force, and now the net torque, which is an origin O, from which we have R plus dr are the distances to minus q and plus q, which are an ideal dipole with distance dr between them. So we use the definition of torque, which is written here. Remember the cross product, okay, here and here. You expand it out, you remember the net force we found in the previous video, and we end up removing higher order effects. So this dE is a higher order, that's why we can neglect it, it's negligible. We end up now having this scenario where if the field is uniform, the net force is 0, so the dynamics is only ruled by the torque, which is P vector E, if I choose O to coincide with the location of minus Q. And then I can have two positions, parallel and anti-parallel, which are stable and unstable respectively for the dynamics of this dipole in an external field. That's it.